The James Webb Space Telescope has captured the first image of galaxies at redshift 13, showing us light from just 400 million years after the Big Bang. Meanwhile, the Event Horizon Telescope has delivered stunning new images of Sagittarius A, our galaxy's central black hole, revealing how these cosmic giants actually shape the formation of stars around them. These 2025 discoveries include updated measurements showing the universe expands at 70.4 kilometers per second per megaparsec, fresh evidence about how the first cosmic structures formed, and revolutionary insights about the forces governing space itself. Today, we'll explore this updated universe using the latest scientific evidence, starting with the most familiar place in the cosmos, our solar system through new eyes. James Webb Space Telescope has captured images showing our solar system with unprecedented clarity. The telescope's infrared capabilities reveal heat signatures from planetary cores that were previously invisible, particularly showing how internal temperature affects planetary dynamics. Mars appears in these new images with surface features detailed enough for scientists to identify mineral compositions across vast regions. Recent observations have fundamentally changed how scientists understand planetary formation in our solar system. The latest data shows that Jupiter migrated inward toward the Sun during its early formation, then reversed direction and moved outward again. This migration pattern explains why Mars is smaller than Earth despite being farther from the Sun. The gravitational effects of Jupiter's movement prevented Mars from accumulating enough material during its formation period. Webb's infrared observations continue to refine our understanding of planetary atmospheres throughout the solar system. The telescope has captured detailed atmospheric data from gas giants, revealing temperature variations and chemical compositions that ground-based telescopes couldn't detect. These measurements help scientists understand how different atmospheric layers interact and how planetary weather systems develop over time. Advanced spectroscopy has produced new measurements of planetary atmospheres that challenge existing models. Europa's water vapor plumes now show consistent traces of phosphorus compounds, suggesting that the Moon's subsurface ocean has chemical ingredients that could support life. Titan's atmosphere contains complex organic compounds, including hydrocarbon chains that form naturally in its upper atmosphere through chemical processes scientists are still working to understand. Recent missions have revealed surprising compositions in asteroids and comets that don't match theoretical predictions. The DART mission's impact with asteroid Dimorphos showed that the asteroid's interior contains significant empty space, making it more like a loose collection of rubble than a solid rock. The Bennu sample return mission found that the asteroid contains water-bearing minerals that formed at low temperatures, proving that some asteroids formed in the cold outer regions of the early solar system. Improved imaging technology has revealed features on familiar planets that weren't visible with previous instruments. Uranus shows seasonal changes in its ring system, with the rings becoming brighter during the planet's long summer season. Pluto's surface shows evidence of geological activity, with nitrogen glaciers that flow slowly across the surface, carving valleys and depositing materials in patterns similar to Earth's glacial systems. The outer solar system and Kuiper belt objects display characteristics that scientists are still working to understand. Eris, the dwarf planet that's larger than Pluto, has a surface covered in methane ice that reflects almost all sunlight, making it one of the most reflective objects in the solar system. The object Arakoth shows that some Kuiper belt objects formed through gentle collisions rather than violent impacts, suggesting that the early solar system experienced less chaos than previously thought. Updated statistics show that our solar system contains 290 confirmed moons, an increase from previous counts. Jupiter has 95 confirmed moons, with the 4 largest showing evidence of subsurface liquid water. Saturn's moon Enceladus ejects hundreds of pounds of water vapor per second from its south pole, creating a ring of water ice particles that orbits Saturn. Even some asteroids have their own moon systems, with small objects orbiting larger asteroids in complex gravitational relationships. The 2025 data reveals that our solar system is more unique than scientists previously understood. Most star systems discovered so far contain hot Jupiter planets that orbit extremely close to their parent stars, but our Jupiter orbits at a distance that allowed terrestrial planets to form in the inner system. The spacing between our planets follows mathematical patterns that don't appear in most other planetary systems discovered by astronomers. The outer reaches of our solar system extend far beyond Neptune into regions that contain thousands of icy objects. The Oort cloud, a spherical shell of comets that surrounds our solar system, begins at a distance thousands of times farther from the Sun than Earth and extends halfway to the nearest star. This region contains an estimated trillion comets, with a total mass equivalent to several Earth masses. Recent measurements show that our solar system moves through space at incredible speeds relative to the cosmic microwave background radiation. This motion creates subtle but measurable effects on planetary temperatures. The entire solar system orbits the center of the Milky Way galaxy once every 230 million years, completing roughly 20 orbits since Earth formed 4.6 billion years ago. These detailed observations of our solar system provide the foundation for understanding planetary formation and evolution. As telescopes become more powerful and detection methods improve, scientists can apply these lessons to study worlds orbiting other stars, searching for systems that might harbor conditions similar to those that allowed life to develop on Earth. The Exoplanet Revolution of 2025. The James Webb Space Telescope has achieved a groundbreaking milestone by capturing the first direct image of a previously unknown exoplanet. This discovery represents a fundamental shift in how astronomers study worlds beyond our solar system, moving from indirect detection methods to actually seeing these distant planets with unprecedented clarity. The newly imaged planet TWA-7b has a mass comparable to Saturn and orbits within a disk of rocky debris 55 light-years from Earth. Direct imaging allows scientists to study planetary formation processes and measure the infrared radiation emitted by planets themselves rather than relying on transit observations or gravitational wobble measurements. The telescope's coronagraph technology blocks starlight to reveal nearby objects, overcoming the challenge of observing planets that are millions of times dimmer than their parent stars. This breakthrough opens possibilities for imaging much smaller worlds. Scientists expect Webb to capture images of planets with just 10% of Jupiter's mass, bringing us closer to directly observing Earth-sized worlds around other stars. The ability to see exoplanets directly provides information about their atmospheric composition, temperature, and orbital characteristics that indirect methods cannot match. Among recent discoveries, Gliese 12b stands out as the most Earth-like world found to date. Located 40 light-years away, this planet orbits within the habitable zone of its red dwarf star, where liquid water could exist on its surface. The planet receives similar amounts of energy from its star as Earth receives from the Sun, making it a prime candidate for atmospheric studies. Gliese 12b completes an orbit around its star every 12.8 days, and scientists estimate its surface temperature ranges between 32 and 85 degrees Fahrenheit. Speculoos 3b, another Earth-sized world discovered 55 light-years away, presents a different scenario. This planet orbits so close to its star that one side permanently faces the star while the other remains in eternal darkness. The extreme temperature differences between the day and night sides create unique atmospheric dynamics that scientists are studying to understand how heat transfers across tidally locked worlds. James Webb Space Telescope has revolutionized atmospheric analysis by detecting water vapor, carbon dioxide, and methane in exoplanet atmospheres with unprecedented precision. The telescope's infrared instruments can measure the chemical composition of atmospheres by analyzing starlight that passes through them during planetary transits. Recent observations of WASP-96b revealed clouds and haze in its atmosphere along with definitive evidence of water vapor. The planet K2-18b, a sub-Neptune located 124 light-years away, shows signatures of water vapor and possibly hydrogen sulfide in its atmosphere, suggesting the presence of clouds composed of water droplets. The diversity of exoplanets challenges existing theories about planetary formation. Scientists have found planets made entirely of diamond, worlds where it rains liquid iron, and gas giants that orbit their stars in less than one Earth day. TOI 849b is a planet with the mass of Neptune but the size of Earth, creating a density so extreme that scientists struggle to explain how it formed. The planet 55 Cancri E has a surface temperature of 3,600 degrees Fahrenheit and may have an atmosphere made of vaporized rock. Atmospheric analysis has revealed chemical compositions that vary dramatically between different types of exoplanets. Hot Jupiters, gas giants that orbit extremely close to their stars, show evidence of titanium oxide and vanadium oxide in their atmospheres, creating temperature inversions, similar to Earth's stratosphere. Super-Earths, planets larger than Earth but smaller than Neptune, display atmospheres ranging from thick hydrogen envelopes to thin rocky atmospheres similar to Mars. The planet GJ1214b appears to have an atmosphere composed primarily of water vapor, making it a potential ocean world with no solid surface. New detection methods have enabled astronomers to find smaller planets that were previously impossible to observe. The transit photometry method now achieves precision levels that allow scientists to detect planets as small as Mars around nearby stars. Radial velocity measurements can detect the gravitational wobble caused by planets with masses as low as twice that of Earth. Gravitational microlensing has revealed planets orbiting stars thousands of light years away, including free-floating planets that have been ejected from their star systems. Statistical analysis reveals that planetary systems are extremely common throughout the galaxy. Red dwarf stars, which make up 75% of all stars in the galaxy, commonly host small rocky planets in their habitable zones. Data suggests that 1 in 5 Sun-like stars has an Earth-sized planet orbiting within the habitable zone. This means the Milky Way galaxy contains billions of potentially habitable worlds, with the nearest one likely located within 12 light-years of Earth. Machine learning algorithms have accelerated discovery rates by automatically analyzing vast datasets from space telescopes. AI systems can identify planetary transit signals and telescope data thousands of times faster than human astronomers, processing years of observations in hours. The algorithms have discovered planets that human researchers missed, including some that produce extremely subtle signals in stellar brightness measurements. Neural networks trained on confirmed exoplanet data can predict which planetary candidates are most likely to be real planets versus false positives. The combination of improved detection methods, larger telescope surveys, and advanced data analysis techniques has revealed that Earth-like planets are common rather than rare. Conservative estimates suggest that hundreds of millions of potentially habitable planets exist within our galaxy. The nearest potentially habitable world lies within 20 light-years of Earth, close enough for detailed atmospheric studies using current technology. These discoveries transform our understanding of planetary formation and the potential for life throughout the universe, revealing that the cosmic processes that created these diverse worlds operate on scales far grander than our solar system alone. Stellar nurseries and cosmic construction. These diverse planetary systems emerge from stellar nurseries where new stars continue forming throughout the galaxy. James Webb Space Telescope has captured images of star formation regions that reveal the intricate processes governing stellar birth and evolution. The telescope's infrared capabilities penetrate cosmic dust clouds that previously blocked optical observations of star formation regions. Dust particles absorb visible light but allow infrared radiation to pass through, revealing star formation activity hidden within dense molecular clouds. These observations show that dust plays a crucial role in star formation by helping gas clouds cool to temperatures where gravitational collapse becomes possible. The James Webb Telescope's infrared instruments detect protostars embedded in dust cocoons that will eventually disperse as stellar winds clear surrounding material. The intricate process of stellar birth unfolds through gravitational collapse that begins when gas clouds reach critical density thresholds. Molecular hydrogen clouds with temperatures of -420 degrees Fahrenheit start contracting under their own gravity when they contain at least 10 solar masses of material. The collapse accelerates as gravity overcomes gas pressure, creating temperatures that rise to 2,000 degrees Fahrenheit at the core within 50,000 years. Nuclear fusion ignites when core temperatures reach 18 million degrees Fahrenheit, transforming hydrogen into helium and releasing energy that stops further gravitational collapse. This process creates a main sequence star that will burn hydrogen for billions of years, with the exact lifespan depending on the star's initial mass. Star formation rates vary dramatically across different galaxy types based on updated 2025 measurements. Spiral galaxies like the Milky Way produce an average of 3 new stars per year, while elliptical galaxies create fewer than 0.1 stars annually. Irregular galaxies show the highest star formation rates relative to their mass, generating up to 20 stars per year per trillion solar masses of gas. Starburst galaxies undergo periods of intense star formation that produce 100 times more stars than normal, depleting their gas reserves within 100 million years. The Andromeda Galaxy currently forms 0.4 stars per year, significantly lower than the Milky Way's rate, suggesting that older galaxies have consumed most of their star-forming gas. Gravitational wave detectors have provided new insights into stellar evolution by observing the final moments of massive star systems. The merger of 2 neutron stars creates gravitational waves that carry information about stellar core composition and magnetic field strength. These collisions forge heavy elements like gold and platinum in quantities equivalent to several Earth masses within milliseconds. The waves reveal that neutron stars have crusts made of crystallized nuclear matter 100 billion times denser than steel. Binary star systems spiral into each other over millions of years, losing orbital energy by emitting gravitational waves that cause the stars to move closer together at accelerating rates until they merge. Astronomers have discovered stellar objects that challenge traditional classification systems. White dwarf stars have surface temperatures below 80 degrees Fahrenheit, cooler than human body temperature, and emit most of their light in infrared wavelengths. Magnetar stars possess magnetic fields 1 trillion times stronger than Earth's, capable of stripping electrons from atoms at distances of 600 miles. Wolf-Rayet stars burn so intensely that they shed mass equivalent to Earth's weight every year through stellar winds traveling at 2,000 miles per second. Thorn-Zeko objects represent theoretical stars where a neutron star orbits inside a red supergiant's core, creating unique nuclear reactions that produce rare isotopes. Brown dwarf discoveries have expanded our understanding of failed stars that never achieved nuclear fusion. These objects have masses between 13 and 80 times Jupiter's mass, insufficient to sustain hydrogen fusion in their cores. Brown dwarfs cool continuously throughout their lives, starting with surface temperatures of 4,000 degrees Fahrenheit and cooling to 200 degrees Fahrenheit over billions of years. Some brown dwarfs have planetary companions and emit radio waves generated by interactions between their magnetic fields and orbiting objects. The nearest brown dwarf, Lumen 16, lies just 6.5 light-years from Earth and consists of a binary pair that orbits each other every 27 years. Stellar population statistics reveal that the universe contains approximately 200 billion trillion stars distributed across 2 trillion galaxies. Red dwarf stars comprise 75% of all stars, with lifespans exceeding 100 billion years due to their efficient fusion processes. Sun-like stars represent only 7% of stellar populations, but play crucial roles in creating heavy elements through supernova explosions. Massive stars larger than 10 solar masses make up less than 1% of all stars, but produce most of the universe's heavy elements during their brief 10 million-year lifetimes. White dwarf stars, the remnants of sun-like stars, number in the billions within our galaxy alone and will continue cooling for trillions of years. Stellar feedback mechanisms shape galaxy evolution through energy and matter ejection processes. Supernovae explosions release energy equivalent to 10 billion hydrogen bombs, detonating every second for 10 seconds, creating shock waves that trigger new star formation in surrounding gas clouds. Stellar winds from massive stars carry away material at speeds reaching 3,000 kilometers per second, enriching the interstellar medium with heavy elements necessary for planet formation. Active galactic nuclei powered by supermassive black holes can halt star formation across entire galaxies by heating gas to temperatures exceeding 10 million degrees Fahrenheit. Young star clusters create cavities and molecular clouds that span hundreds of light years, regulating the rate at which new stars can form. Stars function as the universe's primary architects by creating and distributing heavy elements essential for planet formation and life. The Big Bang produced only hydrogen and helium, while stars forge carbon, oxygen, silicon, and iron through nuclear fusion processes. Massive stars create elements heavier than iron during supernova explosions, including gold, silver, and uranium found on Earth. Each generation of stars increases the universe's metallicity, the abundance of elements heavier than hydrogen and helium, making rocky planet formation more likely around younger stars. The chemical evolution of galaxies depends on cycles of star formation, element creation, and supernova distribution that have operated for 13.8 billion years since the universe began. These stellar processes create the cosmic architecture that shapes entire galaxies, but the most extreme architects in the universe operate on scales that dwarf even the largest stars. At the centers of galaxies, objects exist that bend space-time itself and control the formation of billions of stars through gravitational forces so intense they challenge our understanding of physics. Black holes, the theme says, universe's most extreme architects. The Event Horizon Telescope has delivered unprecedented images of Sagittarius A*, the supermassive black hole at our galaxy center, revealing details that confirm Einstein's most extreme predictions about gravity in space-time. These images show a ring of glowing plasma 52 million miles across, roughly the size of Mercury's orbit around the Sun, with the black hole shadow appearing perfectly circular as general relativity predicted. The photographs capture matter heated to billions of degrees as it spirals toward the event horizon at tremendous speeds before disappearing forever. Black holes play a fundamental role in galaxy formation by regulating star birth rates and distributing heavy elements throughout cosmic space. Supermassive black holes at galaxy centers grow simultaneously with their host galaxies, maintaining a mass ratio of 1 to 700 between the black hole and the galaxy's central bulge. This relationship suggests that black holes and galaxies evolve together through feedback processes that scientists are still working to understand. When black holes consume matter, they release energy equivalent to converting 10% of that matter into pure energy, compared to nuclear fusion, which converts just 0.7% of matter into energy. This energy heats surrounding gas to temperatures exceeding 100 million degrees Fahrenheit, preventing new star formation in regions spanning thousands of light years. Gravitational wave observatories have detected dozens of black hole mergers, revealing that these cosmic collisions happen far more frequently than scientists previously calculated. The most massive merger observed involved black holes with 85 and 66 solar masses, creating a final black hole of 142 solar masses and releasing energy equivalent to 9 solar masses converted directly into gravitational waves. These waves travel at the speed of light and cause space itself to stretch and compress by distances smaller than 1/10 Elson-nth the width of a proton. The LIGO and Virgo detectors can measure these tiny distortions, providing information about black hole spins, masses, and orbital dynamics that cannot be obtained through electromagnetic observations. Recent observations show that black holes create cosmic structures rather than simply destroying them. Black hole jets, streams of particles moving at nearly the speed of light, compress gas clouds and trigger star formation across vast distances. Some black holes act as cosmic seeds that attract surrounding matter and eventually become the centers of new galaxies. Computer simulations demonstrate that without black holes, galaxies would form chaotic structures lacking the organized spiral arms and stellar distributions observed in the universe today. New measurements reveal that supermassive black hole masses correlate precisely with their host galaxy properties. The black hole at the center of the Milky Way has a mass 4.1 million times greater than the Sun, while the galaxy itself contains 100 billion stars with a total mass of 60 billion solar masses. Larger galaxies contain proportionally more massive black holes, with some reaching 66 billion solar masses in the most massive elliptical galaxies. This relationship extends down to smaller galaxies, where black holes with masses of just 100,000 suns still influence star formation across the entire galaxy. The correlation suggests that black holes and galaxies grow through the same physical processes, sharing matter and energy throughout their evolution. Astronomers have confirmed the existence of intermediate-mass black holes with masses between 100 and 100,000 times the Sun's mass. These objects were predicted by theory but remained elusive until recent observations identified them in globular clusters and dwarf galaxies. The black hole in the globular cluster 47 to Tucany has a mass 2,200 times the Sun and influences the motion of nearby stars across a region 20 light-years in diameter. These discoveries fill the gap between stellar mass black holes formed from collapsed stars and supermassive black holes found in galaxy centers. Updated models describe how matter behaves in the extreme environment near black hole event horizons, where gravitational forces stretch objects into thin strands through a process called spaghettification. At the event horizon of a stellar mass black hole, tidal forces would stretch a human body to 200 times its normal length while compressing it to 1/200 its normal width. Time dilation effects become extreme near black holes, with clocks running 50% slower at a distance of 3 event horizon radii compared to clocks far from the black hole. Matter falling into a black hole experiences gravitational redshift that stretches light wavelengths, making objects appear redder and dimmer as they approach the event horizon until they fade from view completely. The 2025 observations have refined scientific understanding of space-time curvature around black holes to unprecedented precision. Einstein's general relativity predicts that space and time become severely warped near massive objects, and black holes represent the extreme limit of this warping. Light rays bend by 90 degrees when passing within 3 event horizon radii of a black hole, and particles can orbit black holes in stable circular paths at specific distances from the event horizon. These measurements confirm Einstein's equations while revealing the fundamental nature of gravity in its most extreme form. The paradoxical nature of black holes emerges clearly from recent research showing that these ultimate destroyers simultaneously serve as cosmic creators. Black holes consume matter and energy while simultaneously generating the conditions necessary for galaxy formation, star birth, and the distribution of heavy elements throughout the universe. They represent both the endpoint of stellar evolution and the beginning of galactic evolution, destroying individual stars while nurturing entire cosmic ecosystems. This duality positions black holes as fundamental architects of cosmic structure, but their influence extends far beyond individual galaxies to shape the largest structures in the universe through gravitational galaxy clusters and cosmic web architecture. These gravitational effects extend beyond individual systems to create the largest known structures in the observable universe. Galaxy clusters represent massive cosmic formations where thousands of galaxies gather together under the influence of dark matter's invisible framework. The Event Horizon Telescope has demonstrated advanced multicoloring techniques that reveal structural details in cosmic objects previously impossible to observe. This technological breakthrough allows astronomers to separate different physical processes occurring simultaneously in the same region of space, providing clearer images of complex cosmic environments. The technique applies frequency phase transfer methods that enhance image resolution and contrast, making it possible to distinguish between different types of matter and energy interactions within the same observational field. Galaxy clusters contain thousands of individual galaxies held together by gravitational forces that span distances of millions of light-years. The Coma cluster extends across 20 million light-years and contains over 1,000 galaxies, with a combined mass equivalent to 1 quadrillion suns. Most of this mass exists as dark matter, which appears in gravitational lensing observations as regions that bend light from background galaxies. The Bullet cluster provides direct evidence for dark matter's existence by showing 2 galaxy clusters that collided 150 million years ago, separating the dark matter from normal matter and proving that dark matter interacts only through gravitational forces. Dark matter creates the fundamental architecture that determines where galaxies form and how they evolve over cosmic time. Computer simulations show that dark matter began clumping together within the first 100,000 years after the Big Bang, creating density fluctuations that grew through gravitational attraction over billions of years. Normal matter follows dark matter's gravitational influence, flowing toward regions where dark matter concentrations provide the strongest gravitational pull. The ratio of dark matter to normal matter remains consistent at approximately 5:1 across all cosmic scales, from individual galaxies to massive clusters containing thousands of member galaxies. Galaxy collisions within clusters create dramatic transformations that reshape entire galactic systems over hundreds of millions of years. The antennae galaxies demonstrate two spiral galaxies currently merging, with gravitational forces creating extended tidal streams that stretch across 500,000 light-years. These collisions compress gas clouds and trigger intense star formation episodes as material heats to temperatures exceeding 10 million degrees Fahrenheit. The collision has produced over 1,000 massive star clusters within the past 200 million years, fundamentally altering both galaxy structures and star formation rates. The space between galaxies contains hot gas heated to temperatures between 1 million and 100 million degrees Fahrenheit through gravitational compression and shock waves from galaxy interactions. This intergalactic medium emits X-rays that reveal its presence and allows scientists to measure temperature, density, and chemical composition across vast regions. The Perseus cluster's intergalactic medium contains heavy elements like iron and silicon created by supernova explosions in member galaxies billions of years ago, showing how stellar processes enrich the space between galaxies with materials necessary for future star and planet formation. Gravitational lensing effects created by massive galaxy clusters function as natural telescopes that magnify and distort images of background galaxies located billions of light-years away. The cluster Abell 2744 creates multiple images of the same background galaxy, with some images appearing 10 times brighter than they would without gravitational magnification. Strong lensing occurs when light from distant objects passes directly through cluster centers, creating arc-shaped distortions and Einstein rings around foreground clusters. These lensing measurements have revealed some of the most distant galaxies in the universe, including objects that formed when the universe was less than 5% of its current age. Galaxy formation occurs preferentially in regions where dark matter density exceeds the cosmic average by factors of 10 to 100. Gas flows toward these high-density regions, where galaxy clusters eventually develop through hierarchical merging processes that continue over billions of years. The rate of galaxy formation correlates directly with local dark matter density, with high-density regions producing more massive galaxies at earlier cosmic times. Galaxies acquire rotational motion through gravitational interactions with surrounding dark matter structures, explaining why most galaxies rotate and develop organized spiral arm patterns. Computer simulations of structure formation reproduce observational data with remarkable accuracy by incorporating dark matter physics, gas dynamics, and stellar feedback processes. The Millennium simulation tracked 10 billion dark matter particles over 13.6 billion years of cosmic history, creating virtual galaxy distributions that match real astronomical surveys. These simulations predict galaxy cluster masses, shapes, and merger rates that agree with gravitational lensing measurements and X-ray observations from space telescopes. The results confirm that structure formation follows a hierarchical pattern where small objects merge to create progressively larger systems over cosmic time. Recent computational advances allow scientists to simulate cosmic volumes containing millions of galaxies while resolving individual star formation regions within each galaxy. The Eagle simulation reproduces the observed relationship between galaxy mass and star formation rate by including supernova feedback that regulates gas cooling and star formation efficiency. These simulations show how galaxy clusters grow through accretion of smaller groups falling along gravitational pathways at velocities reaching 2,000 kilometers per second. The network of galaxy clusters and cosmic structures creates a vast framework that organizes matter across the observable universe. This architecture emerged from quantum fluctuations in the early universe that grew through gravitational amplification over 13.8 billion years of cosmic evolution. Understanding how matter organizes on these largest scales reveals the cosmic environment where galaxies, stars, and planets form and evolve. However, measuring the precise rate at which this cosmic framework expands presents scientists with conflicting results that challenge our understanding of the universe's fundamental properties. The expanding universe, new measurements, and mysteries. Scientists face a major problem when measuring how fast the universe expands because different methods produce conflicting results. The Hubble Space Telescope measures the expansion rate by observing nearby supernovae and Cepheid variable stars, calculating a value of 73 kilometers per second per megaparsec. Meanwhile, measurements from the cosmic microwave background radiation suggest the expansion rate is 67.4 kilometers per second per megaparsec. This 9% difference might seem small, but it represents a fundamental disagreement about the universe's basic properties. The discrepancy has persisted for over a decade despite improvements in measurement techniques, creating what scientists call the Hubble tension. Professor Wendy Friedman has led efforts to resolve this measurement conflict using data from both the James Webb Space Telescope and the Hubble Space Telescope. Her team's latest calculation finds a value of 70.4 kilometers per second per megaparsec, plus or minus 3%. This result brings the supernovae measurements into statistical agreement with cosmic microwave background data, which shows 67.4 plus or minus 0.7%. The convergence suggests that the standard model of cosmology remains a valid framework for understanding the universe's expansion. The James Webb Space Telescope has significantly improved the accuracy of distance measurements, which is crucial for determining the Hubble constant. Webb's high precision, better resolution, and sensitivity, particularly its ability to see through cosmic dust, have allowed for more accurate measurements of stellar brightness in distant galaxies. The telescope's infrared capabilities penetrate cosmic dust that previously obscured stellar observations, allowing accurate brightness measurements of Cepheid variable stars that serve as distance markers. These pulsating stars correlate their brightness directly with their pulsation periods, enabling distance calculations accurate to within 2%. The South Pole Telescope completed its SPT-3G survey, mapping cosmic microwave background radiation across 1/25th of the sky with resolution surpassing previous measurements. The data, taken in 2019 and 2020, covers about 1/25th of the sky, mapping it in more detail than any other measurement of this kind. The Atacama Cosmology Telescope released its final major data set after years of observations, offering another independent check on early universe conditions. These multiple measurement techniques allow scientists to cross-verify results and identify potential systematic errors that might affect individual methods. The cosmic distance ladder represents a series of steps that build upon each other to determine distances to increasingly far-away objects. The Hubble Space Telescope has been instrumental in refining this measurement system over the past 34 years, improving the accuracy of expansion rate measurements to less than 1%. This precision has narrowed the age of the universe to 13.8 billion years by measuring important milepost markers known as Cepheid variable stars. The HST Key project, completed in the early 2000s, provided a value of approximately 72 kilometers per second per MPC with an uncertainty of about 10%. Type A supernovae provide distance measurements to galaxies billions of light years away, with brightness variations now understood well enough to achieve 3% precision. Each supernova explosion releases the same amount of energy, making them visible across cosmic distances exceeding 10 billion light years. Recent observations show that supernova brightness follows consistent patterns regardless of their host galaxy properties, confirming their reliability as distance indicators. These stellar explosions appear dimmer than expected if the universe expanded at a constant rate, proving that expansion has accelerated over the past 5 billion years. The acceleration began when the universe was approximately half its current age, coinciding with a period when dark energy became the dominant component of cosmic energy density. Current measurements show that dark energy comprises 68% of the universe's total energy content, while matter contributes only 32%. The equation of state parameter for dark energy equals -1 within measurement uncertainties, consistent with Einstein's cosmological constant. Dark energy exhibits negative pressure that creates repulsive gravitational effects, driving the universe's accelerating expansion against the attractive force of gravity. New insights about the universe's geometry emerge from precision measurements of cosmic microwave background anisotropies and large-scale structure distributions. The universe's curvature parameter equals 0 within measurement uncertainties of 0.001, indicating nearly perfect flat geometry on cosmic scales. This flatness requires the total energy density to equal the critical density within 1 part in 100,000, a remarkable fine-tuning that supports cosmic inflation theories. The Sound Horizon scale imprinted in cosmic microwave background patterns provides a standard ruler for measuring cosmic geometry. The observable universe's size depends critically on expansion rate measurements, with current estimates placing the cosmic horizon at 46.5 billion light-years radius. This distance exceeds the universe's 13.8 billion year age because space itself has expanded while light traveled toward Earth from distant sources. The comoving distance to the cosmic microwave background surface reaches 45.7 billion light-years, representing the farthest distance from which we can receive electromagnetic radiation. The particle horizon encompasses a volume containing approximately 2 trillion galaxies. The new data from the South Pole Telescope and the Atacama Cosmology Telescope sharpen measurements while confirming the Hubble tension independently at very high statistical significance. These findings remain consistent with other cosmic microwave background constraints, providing cross-checks on our fundamental model of the universe. The convergence of different measurement methods suggests that systematic errors are not the primary source of previous discrepancies, supporting the reliability of current expansion rate determinations. These precision measurements of cosmic expansion establish the framework for understanding how the universe evolved from its earliest moments to its current state. The resolved Hubble tension confirms that our standard cosmological model accurately describes the universe's behavior across vast scales of space and time. However, the most direct evidence for this cosmic history comes from ancient light that has traveled across the entire observable universe, carrying detailed information about conditions when the cosmos was just beginning to take its current form. Cosmic microwave background, echoes of creation. The Atacama Cosmology Telescope has delivered the most detailed cosmic microwave background maps ever created, covering 19,000 square degrees of sky with resolution 5 times sharper than previous space-based measurements. These maps reveal temperature variations as small as 0.00001 degrees across the entire cosmic background, showing patterns that formed when the universe was just 380,000 years old. The South Pole Telescope's SPT-3G survey has completed its observations after years of data collection, providing independent measurements that cross-check results from other facilities. These ancient photons carry information about cosmic conditions from the time when atoms first formed and the universe became transparent to light. Before this moment, the universe was a hot, dense plasma where photons could not travel freely because they constantly scattered off free electrons. When temperatures dropped below 3,000 degrees Fahrenheit, electrons combined with protons to form neutral hydrogen atoms, allowing photons to stream freely through space for the first time. These photons have been traveling toward Earth for 13.8 billion years, cooling from visible light to microwave radiation as the universe expanded. The latest observations provide updated constraints on cosmic inflation theory, which proposes that the universe underwent exponential expansion during its first fraction of a second. Inflation predicts that quantum fluctuations during this expansion phase created the density variations observed in the cosmic microwave background. The measured fluctuation amplitude matches inflation predictions within 2%, supporting the theory while ruling out alternatives that predict different fluctuation patterns. The spectral index of fluctuations equals 0.965 with an uncertainty of 0.004, consistent with the simplest inflation models. New measurements from these observations have refined calculations of the universe's fundamental properties with unprecedented accuracy. The cosmic microwave background data shows that ordinary matter comprises 4.9% of the universe's total energy content. Dark matter accounts for 26.8%, and dark energy makes up 68.3%. The universe's expansion rate at the time of photon decoupling was 67.4 kilometers per second per megaparsec, providing a completely independent measurement of cosmic expansion. These measurements constrain the universe's geometry to flat within 0.1%, confirming that the total energy density equals the critical density required for flat spacetime. Temperature fluctuations in the cosmic microwave background reveal the seeds from which all cosmic structures eventually grew through gravitational amplification. The largest temperature variations span 10 degrees across the sky and represent sound waves that traveled through the early universe's plasma at 57% the speed of light. These acoustic oscillations created alternating regions of higher and lower density that appear as hot and cold spots in the microwave background. Smaller fluctuations, measuring just 0.1 degrees across, mark the locations where the first galaxies would form billions of years later. The 2025 observations have subjected fundamental physics theories to the most stringent tests possible using cosmic data. The measurements confirm Einstein's general relativity on cosmic scales while constraining alternative gravity theories that predict different cosmic microwave background patterns. The data tests whether the speed of light has remained constant over cosmic time, finding no evidence for variation at the level of 1 part in 100,000. Measurements of the cosmic microwave background's blackbody spectrum confirm that the universe was once in thermal equilibrium with precision exceeding 1 part in 50,000. Meanwhile, the Event Horizon Telescope has achieved groundbreaking advances in imaging technology that complement these cosmic microwave background discoveries. The telescope has demonstrated advanced frequency, phase transfer multicoloring techniques that reveal structural details in cosmic objects previously impossible to observe. This technological breakthrough allows astronomers to separate different physical processes occurring simultaneously in the same region of space, providing clearer images of complex cosmic environments. The technique enhances image resolution and contrast, making it possible to distinguish between different types of matter and energy interactions within the same observational field. The Event Horizon Telescope's images of Sagittarius and Asterisk represent the culmination of years of technological development in radio astronomy. The telescope network spans the globe, creating an Earth-sized virtual telescope with resolution capabilities that exceed any single instrument. The images show a ring of glowing plasma with the black hole shadow appearing perfectly circular as general relativity predicted. These observations confirm Einstein's most extreme predictions about gravity and space-time while revealing how matter behaves in the universe's most extreme gravitational environments. The story told by these ancient photons reveals a universe that began in extremely hot, dense state and has been expanding and cooling for 13.8 billion years. The cosmic microwave background captures the moment when the universe transformed from an opaque plasma into the transparent cosmos we see today, preserving information about the conditions and processes that shaped cosmic evolution. These photons have traveled farther than any other electromagnetic radiation, carrying messages from the universe's infancy across billions of light years and billions of years to reach Earth's telescopes. The patterns revealed by both cosmic microwave background observations and black hole imaging demonstrate that the universe began with remarkable uniformity, marked only by tiny fluctuations that grew into the rich structure of galaxies, stars, and planets that surround us today. These measurements provide the foundation for understanding how cosmic structures formed and evolved over billions of years. The precision achieved by current observations allows scientists to trace the universe's development from its earliest moments through the formation of the first cosmic structures that would eventually become the galaxies we observe today. The first galaxies, windows to cosmic dawn. The James Webb Space Telescope has captured images of galaxies that formed when the universe was just 400 million years old. revealing cosmic structures that existed much earlier than scientists thought possible. These ancient galaxies appear as red dots in the telescope's infrared images, their light stretched by 13.4 billion years of cosmic expansion from blue and ultraviolet wavelengths to the infrared spectrum. The galaxy JHGS Z13-0 formed when the universe was only 325 million years old, making it one of the most distant objects ever observed at redshift 13. Another galaxy, JHGS Z11-0, shows signs of active star formation occurring just 400 million years after the Big Bang. These observations push back the timeline of galaxy formation by hundreds of millions of years compared to previous estimates based on Hubble Space Telescope data. The light from JHGS Z13-0 has traveled for 13.4 billion years to reach Earth, meaning we observed this galaxy as it appeared when the universe was less than 3% of its current age. The galaxy appears extremely compact, measuring just 1,600 light-years across compared to the Milky Way's 100,000 light-year diameter. Despite its small size, spectroscopic analysis reveals active star formation occurring at rates that challenge current understanding of early cosmic evolution. Webb's infrared capabilities allow astronomers to peer through cosmic dust that previously obscured these ancient objects from optical telescopes. The telescope's near-infrared camera captures light that has been redshifted from ultraviolet and visible wavelengths into the infrared spectrum due to cosmic expansion. This redshift effect stretches the wavelength of light proportionally to the distance it has traveled, with the most distant galaxies appearing deep red in Webb's images. The redshift measurements provide precise distance calculations, with JS G13-0 showing a redshift value of 13.2, corresponding to a look-back time of 13.4 billion years. Spectroscopic analysis of these early galaxies reveals chemical compositions that reflect the universe's primordial state. The first generation of stars formed from hydrogen and helium gas left over from the Big Bang, without any heavy elements that characterize later stellar populations. These massive stars burn through their nuclear fuel in just a few million years before exploding as supernovae that enriched surrounding gas with carbon, oxygen, and iron. Webb observations detect galaxies with extremely low metallicity, indicating they formed shortly after the first stars died and began the process of cosmic chemical enrichment. The galaxy GNZ11, observed at redshift 10.6, provides detailed insights into star formation processes in the early universe. This galaxy formed when the universe was approximately 420 million years old and shows evidence of extremely active star formation despite its compact size. The stellar population consists almost entirely of young, massive stars that burn blue and hot, giving these galaxies distinctive ultraviolet signatures that Webb detects in the infrared after cosmic redshift. Gas fractions in these early galaxies exceeded 50% of their total mass, providing abundant fuel for rapid star formation. Evidence for cosmic reionization emerges from these observations, showing how early stars and galaxies heated and ionized the universe's neutral hydrogen gas. The intergalactic medium remained neutral for approximately 150 million years after the cosmic microwave background was emitted, creating a cosmic dark age when no stars had yet formed. Early galaxies produced ultraviolet radiation that gradually ionized surrounding hydrogen gas, creating expanding bubbles of ionized space around each galaxy. Webb data suggests that faint galaxies contributed more to reionization than previously estimated, with millions of small galaxies collectively producing enough ionizing radiation to clear the cosmic fog. These ancient galaxies differ dramatically from their modern counterparts in size, shape, and star formation activity. Early galaxies appear more compact and irregular, lacking the organized spiral structure common in today's galaxy populations. The average early galaxy measures just 2,000 light-years across, with star formation occurring throughout the galaxy rather than being concentrated in spiral arms or nuclear regions. The stellar populations consist almost entirely of young, massive stars, creating distinctive spectral signatures that distinguish them from older, redder modern galaxies. Updated timelines show that cosmic structure formation began much earlier than previously thought, with the first stars forming just 180 million years after the Big Bang. The cosmic dark age ended when the first stars ignited nuclear fusion and began producing heavy elements through stellar nucleosynthesis. Galaxy formation accelerated rapidly after 300 million years, with the first massive galaxies assembling within 200 million years of the first star formation. These revised timelines suggest that the universe evolved more rapidly during its first billion years than during any subsequent period. The implications for cosmic evolution include revised understanding of how galaxies, stars, and heavy elements formed during the universe's first billion years. Early galaxies produced heavy elements more rapidly than previously calculated, enriching the intergalactic medium with carbon, oxygen, and iron within 500 million years of the Big Bang. These observations provide direct evidence of cosmic conditions that existed over 13 billion years ago, revealing how the universe transformed from a dark neutral medium into the structured cosmos filled with stars and galaxies. Witnessing the universe's childhood through these ancient galaxies provides the deepest view into cosmic history ever achieved. The light from these galaxies has traveled across space for 97% of the universe's current age, carrying information about stellar populations, gas compositions, and formation processes from cosmic dawn. These observations reveal the visible components of early cosmic structure formation, yet they represent only a small fraction of the matter and energy. Dark matter and dark energy, the universe's hidden majority. Most of the cosmic structures we observe represent only the visible tip of a vast hidden reality that governs the universe's behavior and evolution. We can observe only 5% of everything that exists in the universe through telescopes and other instruments. The remaining 95% consists of dark matter and dark energy, mysterious components that interact with regular matter only through gravitational forces. Precision measurements from the Planck satellite have determined the universe's composition with unprecedented accuracy. Normal matter, which forms stars, planets, and everything we see, accounts for just 4.9% of the universe's total energy content. Dark matter comprises 26.8%, while dark energy makes up 68.3% of cosmic energy density. These percentages come from the most precise cosmic microwave background radiation measurements ever achieved, with uncertainties smaller than 1%. The South Pole Telescope's SPT-3G survey has provided independent confirmation of these proportions through observations covering approximately 1/25th of the sky, with sensitivity exceeding all previous measurements taken from space or ground-based observatories. Gravitational effects provide the strongest evidence for dark matter's existence through observations of galaxy rotation curves and gravitational lensing phenomena. Spiral galaxies rotate too fast for their visible matter alone to hold them together, requiring additional invisible mass to prevent stars from flying apart. The galaxy rotation problem appears in thousands of galaxies where stars at the outer edges move at speeds that should tear the galaxy apart without dark matter's gravitational influence. Galaxy clusters show similar effects, with member galaxies moving too fast to remain bound by the gravity of visible matter alone. The bullet cluster collision demonstrates dark matter's presence by showing how gravitational effects separate from normal matter during the collision between two massive galaxy clusters. X-ray observations reveal hot gas from normal matter, while gravitational lensing maps show where the invisible mass actually resides. The clear separation between these components provides some of the strongest evidence for dark matter's existence as a distinct physical substance rather than a modification of gravitational physics. Dark energy drives the universe's accelerating expansion by exerting negative pressure that creates repulsive gravitational effects throughout space. Type Ia supernovae observations in distant galaxies revealed that cosmic expansion has been accelerating for the past 5 billion years rather than slowing down as expected from matter's gravitational pull. These supernova explosions serve as standard candles because they all release the same amount of energy, allowing astronomers to measure distances to galaxies billions of light years away. The James Webb Space Telescope has refined distance measurements to nearby galaxies, helping resolve discrepancies between different methods of measuring cosmic expansion rates. Professor Wendy Friedman's latest calculations using both Webb and Hubble data find a Hubble constant value of 70.4 kilometers per second per megaparsec plus or minus 3%. This result brings the supernovae measurements into statistical agreement with cosmic microwave background data, confirming that the standard lambda-CDM cosmological model accurately describes the universe's expansion. Recent observations have constrained dark matter and dark energy properties through measurements of cosmic microwave background radiation patterns. The cosmic microwave background reveals how dark matter influenced structure formation during the first 380,000 years after the Big Bang. Temperature fluctuations in this ancient light show the imprint of dark matter density variations that eventually grew into the cosmic web of galaxies and galaxy clusters. These measurements provide independent confirmation of the lambda-CDM cosmological model while testing alternative theories about dark energy's behavior over cosmic time. The DESI survey measurements indicate a preference for evolving dark energy rather than Einstein's cosmological constant, though these results remain within statistical uncertainties of the standard model. The survey measures baryon acoustic oscillations and galaxy clustering patterns, providing another independent check on cosmic composition. However, the standard lambda-CDM model remains the most consistent with current data from multiple independent sources. Computer simulations of dark matter structure formation now reproduce observational data with remarkable accuracy by modeling the gravitational interactions of billions of dark matter particles over cosmic time. These simulations show how dark matter forms a cosmic web of filaments and nodes where galaxies eventually form through gas cooling and star formation processes. The results confirm that dark matter provides the gravitational scaffolding necessary for cosmic structure formation while revealing how galaxies acquire their observed properties. Future missions will attempt to identify dark matter and dark energy through multiple complementary approaches, including precision cosmological measurements. The Nancy Grace Roman Space Telescope will measure cosmic expansion through observations of Type Ia supernovae and gravitational lensing effects across billions of galaxies. The Euclid mission will map dark matter distributions through weak gravitational lensing that slightly distorts background galaxy shapes. Ground-based telescopes like the Vera Rubin Observatory will discover thousands of supernovae and measure baryon acoustic oscillations and galaxy clustering patterns. These missions will test whether dark energy properties remain constant over cosmic time or evolve in ways that might reveal its fundamental nature. The measurements will provide independent expansion measurements that cross-check results from different observational techniques. The Euclid mission is specifically designed to map the geometry of the dark universe and constrain the equation of state parameter for dark energy. The humbling reality emerges that 95% of the universe consists of components whose fundamental nature remains largely unknown despite decades of intensive research. Scientists can measure dark matter and dark energy's effects on cosmic evolution with exquisite precision while understanding only their gravitational influences. This situation represents one of the most profound mysteries in science, where the vast majority of existence operates through mechanisms that remain hidden from direct observation. Yet these invisible components have shaped every structure we observe, from the smallest galaxies to the largest cosmic web filaments, creating the framework within which all visible matter organizes itself across the observable universe. The boundaries of what we can directly observe, however, may represent only the beginning of an even more extraordinary cosmic reality. Beyond the observable universe, theoretical frontiers. Theoretical physics suggests that reality extends far beyond what our telescopes can reveal, pushing the boundaries of scientific inquiry into realms that may forever remain beyond direct observation. Our cosmic horizon marks the boundary of everything we can possibly observe, extending 46.5 billion light-years in all directions and encompassing everything from which light has had time to reach Earth since the Big Bang. This boundary exists not because space ends there, but because we cannot receive information from regions farther away due to the finite age of the universe and the speed of light. The concept of what lies beyond the observable universe remains one of the most captivating topics in modern cosmology, challenging our fundamental understanding of cosmic boundaries and the very nature of reality. Scientists explore the limits of current knowledge through theoretical frameworks that attempt to describe what might exist in regions forever hidden from our view. These investigations force us to consider whether our universe represents the entirety of existence or merely one component of something vastly larger. Inflation theory provides a scientific foundation for considering regions beyond our observable universe by describing how rapid cosmic expansion in the early universe could generate multiple distinct areas of space. The inflationary epoch lasted from 10 to the power of negative 36 to 10 to the power of negative 32 seconds after the Big Bang, during which space expanded faster than the speed of light by factors exceeding 10 to the power of 26. This expansion stretched quantum fluctuations to cosmic scales, creating the density variations that eventually became galaxies and galaxy clusters. Some theoretical models suggest that inflation never completely stops throughout all of space, continuously creating new regions that undergo their own expansion events. Each expanding region could become a separate cosmic domain with its own space, time, and potentially different physical constants. This process might resemble the formation of bubbles, with each bubble representing an independent cosmic region within a larger structure that extends beyond our observational capabilities. Current scientific thinking addresses whether the universe is finite or infinite through observations of cosmic geometry and theoretical considerations about spatial topology. Measurements of cosmic microwave background anisotropies indicate that space has flat geometry within observational uncertainties of 0.4%, suggesting that the universe could extend infinitely beyond our observable horizon. If space is truly infinite, then the implications become profound for understanding the total scope of cosmic reality. The mathematical frameworks developed to describe these scenarios draw from string theory and quantum field theory, which naturally produce predictions about regions beyond our direct observation. String theory allows for different configurations of extraspatial dimensions, each potentially creating cosmic domains with distinct physical properties. These mathematical structures provide specific frameworks for understanding how different cosmic regions might exist and what their properties could be. Evidence from cosmic microwave background radiation patterns reveals subtle anomalies that standard cosmological models struggle to explain completely. The Wilkinson Microwave Anisotropy Probe and Planck satellite detected unexpected features in the cosmic microwave background, including temperature asymmetries between different hemispheres of the sky. The South Pole Telescope's latest observations have refined measurements of these anomalies, though scientists continue investigating whether they represent signatures of physics beyond our current understanding. Quantum mechanics introduces additional theoretical possibilities through interpretations that suggest reality might branch into multiple parallel versions. The many-worlds interpretation proposes that every quantum measurement could split the universe into separate realities corresponding to all possible measurement outcomes. This process would create an exponentially growing number of parallel cosmic domains, with each branch containing observers who experience only one outcome of each quantum event. The philosophical implications of these theoretical frontiers challenge fundamental concepts about reality, identity, and the uniqueness of human existence within cosmic evolution. If regions beyond our observation contain variations of cosmic evolution, then questions arise about the nature of physical loss, the meaning of individual existence, and our place within the broader cosmic context. The Anthropic principle gains significance in these scenarios, suggesting that we observe a universe with properties suitable for life simply because we exist in a cosmic region where life is possible. These theoretical explorations reveal that our observable universe, with its 2 trillion galaxies and countless stars and planets, might represent just one region within a vastly larger cosmic reality. The boundaries of direct observation may mark not the limits of existence, but rather the beginning of territories that extend far beyond our current ability to explore or understand. The mathematical models describing these possibilities continue evolving as scientists develop new frameworks for understanding cosmic reality beyond observational limits. Advanced computational methods allow researchers to explore the implications of different theoretical scenarios, testing how various models predict the behavior of cosmic regions that remain forever hidden from direct study. Current research focuses on identifying potential signatures that might provide indirect evidence for these theoretical frontiers. Scientists examine cosmic microwave background patterns, gravitational wave data, and large-scale structure measurements for subtle indicators that could reveal information about cosmic reality beyond our observational horizon. These investigations represent some of the most challenging work in theoretical physics, requiring sophisticated mathematical tools and computational resources. The exploration of these theoretical frontiers represents humanity's attempt to understand the full scope of cosmic reality using the tools of mathematics, physics, and scientific reasoning. While direct observation remains impossible for regions beyond our cosmic horizon, theoretical physics provides frameworks for investigating what might exist in these hidden territories and how they might relate to the universe we can observe. These investigations into cosmic reality beyond observation demonstrate how scientific inquiry pushes against the boundaries of the knowable, using theoretical frameworks to explore territories that may forever remain beyond direct study. The work reveals both the power and limitations of human understanding when confronted with the ultimate questions about the nature and extent of cosmic reality. The scientific breakthroughs achieved in 2025 mark a transformative year for astronomy and cosmology. The Event Horizon Telescope delivered the first detailed images of Sagittarius A*, our galaxy's central black hole, confirming Einstein's predictions about space-time curvature with unprecedented precision. The James Webb Space Telescope captured galaxies at redshift 13, showing us cosmic structures that formed just 400 million years after the Big Bang. Professor Wendy Friedman's team resolved the Hubble tension by combining Webb and Hubble data to determine an expansion rate of 70.4 kilometers per second per megaparsec. These discoveries open new windows into cosmic reality, revealing how black holes shape galactic evolution and how the first galaxies formed much earlier than previously thought. The convergence of different measurement techniques confirms our standard cosmological model, while pushing the boundaries